Hi everyone. Today I'd like to review energy diagrams. Okay, these are simply pictures that describe how energy changes during the course of a reaction or some other process, such as rotations about a single bond. So down here we have ethane, and here you can see the three-dimensional shape of it. You got the wedge where the hydrogen is coming towards you, and got the dash bonds, hydrogen's going away. And if you look at this molecule from the side, that's supposed to be an eyeball. So looking at the molecule from the side, from this person, this eyeball's perspective, this hydrogen is right here. And so this carbon right here is this dot in the middle, and the carbon in the back, let's circle it, that's the circle. Okay, and so you can see here that this hydrogen is set in between these two hydrogens, and that's the most stable conformation, the most stable shape of ethane. But single bonds can rotate, so if we rotate, let's see, the back hydrogens this direction, that means we're rotating this carbon about the single bond here, because single bonds allow free rotation. What can happen is the hydrogens can line up and eclipse each other. And in the molecule itself, the electrons surrounding the hydrogens, those electrons are in the covalent bonds, they get closer together and they repel. And so that's a higher energy state. That's more unstable. And so these pictures are trying to show us how that's unstable. And this is more stable. But another way to describe the stability or the energy of the system is to graph it. And that's what's over here on the right. So we graph potential energy vertically. More energy, more unstable is going up. And then on the x-axis, we got degrees of rotation. We're just rotating the molecule about that single bond. And you can see that every time that the hydrogens are passing in front of each other, eclipsing, the energy is high. And then when the hydrogens are staggered in between each other, nicely spread apart, there's less electronic repulsion, the molecule is more stable, and the energy is at a minimum. And if you're somewhere in the middle, like you kind of have these halfway, not totally eclipsing, not totally staggered, then you're some other point on the energy curve. Okay, let's look at another example. Here we're going to describe the energy changes during a chair flip of cyclohexane. First, let's get a little visual by watching a movie of that process of cyclohexane. Well, we say it's a chair flip, but it's more like a wiggle where it goes from one chair conformation to another. So down here we got the chair conformations. You can see that this carbon is up high, this one's down low, and then what we're going to do in the video is move this carbon up. It's going to be up over here on the right, and when that happens, ultimately this carbon on the left will go down. That's this one over here, and we'll go from one chair conformation to the other. Okay, so here's the chair conformation. There's a half chair, a twisted boat, the boat, twisted boat again, half chair, and back to chair. Okay, here we got the chair conformation where the blue hydrogens are axial. That's a very stable configuration. Actually, as you inspect all the hydrogens, they appear to be staggered. As you select any two carbons and look at those hydrogens, they're actually all staggered, so that's very nice and stable. Here is the half chair. Over here on the left, the hydrogens are actually eclipsing each other. So we have some electronic repulsion. This is a higher energy state, not so favorable. And this is the twisted boat. Things are getting a little more crowded. And then it's in the boat, and you got these hydrogens pointing straight up. They're actually pretty close together. We got some other hydrogens that are eclipsing. Yeah, down here in the bottom, there's actually two red and two blue hydrogens totally eclipsing each other, so you can't see them. Back to the other twisted boat. The other half chair. And now we're back to the other chair conformation where the red hydrogens are now axial and the blue are equatorial. And so now we could plot the energy changes during a chair flip. The chair conformation is the most stable, so it's going to be low in energy. That's more stable on our energy diagram, and unstable, more energy, is higher up. Okay, so the chair is most stable. The half chair is really bad. We've got all these eclipsing conformations. The boat, well, as you compare this one to that one, they're actually staggered. But these two are eclipsing, but they're also pointing away from each other. They're not so close. These hydrogens are actually pointing in towards the center. They're getting a little bit crowded. So we have an energy way up here. And then we didn't show, well, this diagram doesn't show the twisted boat. They actually try and bend the molecule a little bit so these hydrogens are not completely eclipsing each other. So it's a little bit lower energy. Okay, and then we get to the other chair conformation and it's low in energy again. And what's nice about the plot here is that you can talk about any point during this motion and get the energy. That's a nice smooth curve. Okay, so allows us to analyze these molecules and predict which shapes are stable and which are less preferred. Okay, now what I like to do is move away from processes like rotations, bond rotations, and chair flips and such, and let's move into reactions. And to do that, let's first review the Gibbs free energy equation, where we have delta G, which well, it's called the Gibbs free energy constant, or change, rather. Its most important feature is that when you calculate a delta G that's negative, it will predict that the reaction or process will be spontaneous, meaning it should happen all by itself. Now, you might remember it needs a little kick to get it going. Let's talk about like a match. A match, lighting is a spontaneous process, but it needs a little bit of heat, a little bit of friction. So a little kick to get going, that's called the activation energy. Now, a little bit of energy, the threshold amount, small amount, minimum amount, needed to get the reaction started. And once it gets started, then the reaction just keeps on going on its own. That is called the activation energy, and I have oftentimes abbreviated just E for energy and ACT as a subscript, activation energy. Sometimes you see E sub A, and then occasionally they'll put a double cross on delta G, and that also implies the activation energy. A couple other terms you need to be aware of. When the delta G is negative and the reaction is spontaneous, you can say that the reaction is exergonic. And then when everything's flipped around, delta G positive, it's not going to be a spontaneous, it's endergonic. And then you might recall that delta H, the enthalpy change, or the heater reaction, has similar terms. Exothermic is when heat comes out. Endothermic is when heat is absorbed during the course of the reaction. And of course there's delta S, the entropy change. It's a measure of randomness or molecular disorder, a couple other things. And the idea is that nature tends to get more disordered as things become more favorable. And so when delta S is positive, randomness increases. Let's see, I think there's a couple more terms here. Right, transition state. I've abbreviated that TS at times, transition state. That's the imaginary point at which a molecule is breaking some bonds and making other bonds. And it's not something you can freeze or see visually, but it's something imaginary, something that we think is happening as the molecule passes from reactants to products. Right? Because during a reaction, we have some bonds that are breaking in the reagents, and we're forming new bonds to form products. So the transition state is when it's making that transition between a reactant and a product. We're breaking some bonds and making new ones. And because these bonds are not completely formed, this is going to be a high energy state, a top of a curve when we graph the energy diagram. Okay, that's a little bit different from an intermediate. An intermediate is something that you could potentially freeze out or capture during the course of a reaction. It's something that is not a completely a pure product, but it does exist temporarily, but then it often reacts again to go to the final products. So intermediates, I define them as a short-lived or temporary product. Okay, let's take a look at a reaction and run through the mechanism. Let's describe how the bonds are breaking in the reactants and new bonds are forming to make a product. So here's a reaction between ethene, right, our simplest alkene, carbon-carbon double bond, and hydrobromic acid. Okay, the mechanism that's proposed is that one of the bonds of the double bond, the pi bond, the pi electrons specifically, will attack H+. And if we think about hydrogen bromine making a covalent bond, well then that's a polar covalent bond. Hydrogen's slightly positive, and the bonding electrons here are attracted to it. And in the course of this first step of the mechanism, this pi bond is going to break and form a new bond to this hydrogen. This hydrogen bromine bond is going to break. That's what this curved arrow is explaining, is hey, these two bonding shared electrons are going to fall onto bromine as a lone pair. And the pi electrons are going to reach out and attach to the hydrogen. Now hydrogen can only make one bond, so it has to choose between bonding the first carbon and the second one, and here it doesn't really matter. The molecule is symmetrical, so it can go to either one. The author of this diagram has chosen the hydrogen to go to the left carbon, and that means this carbon on the right is shortchanged. It's missing a bond. Carbon prefers the bond 4 times. Right here it's only bonding 3 times. And it does not have a lone pair, so it has a formal +1 charge. It's a cation or a carbocation. And this molecule is our first intermediate. Okay, it's a short-lived product. This molecule exists for a brief amount of time after ethene reacts with hydrobromic acid. The bromine that broke away from hydrobromic acid can come back around and then attack the carbocation. And that's pretty straightforward, right? Opposites attract. We got a cation, we got an anion. Opposites attract, and when carbon, a nonmetal, attaches the bromine, a nonmetal, you get a covalent bond. So even though these are charges and they're ions, we don't form an ionic bond, it's covalent. And here's our product. Well, now let's draw the energy diagram for this reaction. Okay, when you're asked to draw the energy diagram, and if you don't have any values for some of the, the bond energies or anything like that, and you don't have any numbers for doing your plotting, then you just use your best judgment. Just make some educated guesses. And all our energy diagrams are going to begin with an X and a Y axis. The X-axis is called the reaction progress. It's how the reaction is progressing. It's sort of like time, but not really, right? Some of these reactions take a long time, others are really quick, and we're not like plotting seconds here. We're just saying, hey, arbitrarily, this reaction is going to proceed starting on the left and ending on the right. Sometimes it's called the reaction coordinate. On the y-axis is energy. Sometimes it's potential energy, sometimes it's delta G, the free energy. Okay. But it's some type of measure of stability and instability, right? More unstable things are, the higher up there are in energy. But nature prefers to become more stable, and so the tendency is to go down and form more stable products. Okay, now you and I are going to start making this energy diagram. We don't have any numbers, so draw your X and Y axis, label them, energy, reaction progress, and then choose a location. Somewhere, not the bottom of the graph, but about a third of the way up or so, an arbitrary height, and draw a line. That's where the energy of the reactants are. I'm going to write reactants, but when you draw the energy diagram, you should actually draw the specific reactants. So here we have ethene and HBr. Okay, those are reactants. And then let's just take care of the first step of the mechanism. Let's break the hydrogen-bromine bond, and let's break the double bond. The only new bond we're going to make is this carbon-hydrogen bond. So making bonds is favorable. It releases energy. Breaking the bonds actually takes energy. So what do you think is happening in this step? Are we going to go up in energy or down in energy? Oh yeah, we're going way up in energy. We're forming something that's pretty unstable, a carbocation, charged, right? Nature likes neutral compounds, but here we're going to make something charged. Not good. We're breaking a double bond and then only getting a single bond out. So our intermediate is not going to be below the energy of the reactants. It's going to be much higher. So I'm going to make it way up here. Here's our intermediate. The product of the first step of the mechanism, it's the carbocation, and again, we should draw it. If this was the end of the reaction, you could talk about the free energy change. It's positive. We go up in energy. And so we would say this is not spontaneous, right? Delta G negative is spontaneous when you go down in energy. Let's draw the energy curve. This is the change in energy from starting to this midpoint, the end of the first step. But we need a little extra kick. We need the activation energy. So the activation energy is going to be higher than both of these bars. It's a little bit extra. And so I just randomly picked this height. It's higher than both. And now what you want to do is connect a curve. You kind of make a dip here for the start of your curve. Pass through this point where you decide the activation energy resides. And then form a little dip at where your intermediate is. And you can kind of clean it up. You can see that it wasn't very rounded here. And I'm still not doing a great job, but you get the idea. So the top of this hill, from where you start, the reactants, to the top of the hill, that's your activation energy. That's the amount of energy it takes to get the reaction going. At the top is that imaginary transition state, the point at which the pi bond is halfway broken, the hydrogen-bromine bond is halfway broken, and the carbon-to-hydrogen bond is halfway formed. Okay, let's keep moving on. We got this intermediate, and it's highly reactive. Oh, and I forgot one other intermediate. We have the bromide ion. Okay, next step, opposites attract. Cation meets anion, and we make a product that's neutral. So where do you think the energy resides? Are we going to go up higher than the intermediate, or are we going to go down lower? We're going to go down lower. We're forming something very stable. And we should think about how low. Should it be higher or lower than the reactant side? Well, that's where you can think about hydrobromic acid. Strong acid, very reactive. That's kind of unstable if it's very reactive. So we're going to get something that's not an acid in the end. That's very neutral, very stable. Yeah, we want to go down way lower. Lower than the reactants. Somewhere down here. This is our product. Maybe I should extend my x-axis here. And again, don't just write the word product. Write the specific product that's made in the course of this reaction. Now, where do we think the activation energy is going to reside? Is it going to be really high? Higher than this one over here on the left? Well, what's happening? What's the transition state look like? Well, it starts by this pair of electrons forming a bond to that carbon. There are no bonds being broken. We're just going to make one bond. At the same time, we're quenching charge. That's a very stabilizing, energy lowering effect. Yeah, there's not going to be much activation energy here. So the hill's not going to be very high. So it's got to be higher than where you start, because it still needs a little kick. You know, maybe the electrons in this bond and that bond are repelling the negatively charged bromine. So it has to kind of squeeze in between those bonds as it approaches the positive charge. So it needs a little help. It needs to collide with this molecule with a little bit of force. But I'm going to make a small hill. Maybe that's my transition state. We are half making the bond between the carbon and the bromine. And then we just dip all the way down the product. There we go. This needs a little bit of cleaning up. But there's our energy diagram. How's this for cleaning up? Yeah, let's go steal the graphic from somewhere else. We got ethene, hydrobromic acid, energy diagram. Here's the transition state, top of the curve. Activation energy, where you start to the top of that hill. And then we got the carbocation intermediate. Carbocation intermediate still here. And then we got a smaller hill, a second transition state right there, top of this hill. And notice that the second activation energy is where you, not where you ultimately began way over here with this reactance, but it starts with the intermediate. You start at this little valley and you need to go over the hill. So how high is the hill relative to where you start at the base of the hill? So it's a small activation energy. So just remember how you measure this. Start from the nearest valley to the nearest hill. That gives you the activation energy. And then we make products. Oh, good point. What's the overall delta G? What is the total free energy change? The total or overall has to consider where you started, way over here, and where you end, way over here. And what happened? We went down in energy. And as you go down, that means delta G is negative. And that means it's spontaneous. So this is a very spontaneous reaction. Happens quite easily in the lab. And now let's ask a question. See how well we understand this. Which of these two steps, the first step to make the carbocation or the second step to make the product, is rate determining? Or in other words, which is faster, which is slower? The slower step is going to determine how fast this reaction goes from reactants to products. To answer this question, consider the activation energy. We got the first activation energy that goes from reactants all the way up to here to make the intermediate. And we have the second activation energy. It starts at the base of this hill and just goes up to this little hill here. So which one is going to be tougher to get over? The big hill. And think about physically walking up this. If this is a real, a trail out in the woods, out in the park somewhere, and you have to walk over this hill, the second hill would not be very difficult. You get over that pretty quickly and to the end of your trail fairly fast. The rate determining step is going to be this first hill. It's the first step that determines how fast this reaction goes. Okay, last concept, catalyst. One more thing to add to the mix. You may already know what a catalyst is. It's something that speeds up a reaction. And that catalyst doesn't get used up, right? You can add more reactants, increase the concentration of reactants. That will speed up a reaction, but of course those reactants then get changed in the products. A catalyst is something that also speeds up a reaction, but at the end of the reaction you can get the catalyst back. Now how does it speed up a reaction? Well, what it does is it lowers the activation energy. A smaller hill means a faster reaction. And so if it's just affecting the hill, the energy diagram, it doesn't affect your products. The catalyst is not supposed to create new products. Or if this is an equilibrium reaction, it's not supposed to change equilibrium, right? You'll have the same ratio of reactants and products. Once the system reaches equilibrium, a catalyst reaches equilibrium faster. Okay, as you look at the energy diagrams here, whoa, what happened? This is just an example. The original reaction is this nice smooth one. It says that, hey, you mix reactants X and Y to make Z. There's no intermediate. All you have to do is get a bunch of activation energy, and somehow the bonds in X and Y break. At the same time, they form and turn into Z. Go over this big activation energy hill, and once you're over that, boom, you go down here. And is this reaction exergonic or endergonic? Or in other words, is it spontaneous? The answer is it's exergonic. It's spontaneous. It started high, goes down low. Delta G is negative. Now, in this imaginary reaction, we can add a catalyst. And now what's going on? Well, the catalyst is changing the mechanism. And it turns out the catalyst can change during the course of the reaction. It's just that by the end of the reaction, it can't be used up. We have to get it back in its original form by the end of the mechanism. And then when the scientist says, hey, what form did I put the catalyst in at the beginning and what form did I get the catalyst back at the end? If they're the same, it appears to be unchanged. But actually it can change during the course of the mechanism, just as long as it changes back. And so with the catalyst, we have a brand new mechanism, and we get 1, 2, 3 intermediates. So what happens? I don't know, X or Y, or maybe both interact with the catalyst to form a brand new short-lived product, and that has a smaller activation energy. So it's a fairly quick step compared to the original one with no catalyst. But then this intermediate pauses here briefly, and then there's another activation energy to get to the second intermediate. But if you look at that activation energy, it's still smaller than this one. So it's still going to be faster. Second intermediate waits a little bit, and there's another activation energy. Change it into an intermediate, third one. But this one is almost done. There's a tiny little activation energy here. It's really quick. This finally changes the product. Okay, I hope that little review of reaction diagrams and energy diagrams is helpful. I'll see you in class.